All right, this is our solutions manual for, or solutions video for the coupled motion worksheet. We have the first problem. We have two blocks. One is mass 1 kilogram, 3 kilograms. And then we have a string in between the 1 and 3 kilogram with the tension of 2 newtons. And we have a force F, which is unknown. And we have been asked to find the force of F, okay? And so what we need to do is we need to have some labels. I'm going to call this block A. I'm going to call this block B. I'm going to draw a free body diagram on A. Oh, this was really important. No friction. Okay, so here's my free body diagram on A. I have force of gravity acting down on A, which is the mass of A times G, which is also known as the weight of A. Let's get rid of that little line. There we go. Okay. We have force normal acting up on A, and we have this force of tension acting on A, which we know is 2 newtons. And then on block B, we have force normal, we have force of gravity acting on B, which is the mass of B times the acceleration due to gravity, which is also called the weight of B. We have this force F pulling to the right, and we have force of tension pulling to the left. And this is the free body diagram of B. What are our knowns? We know force of tension, which is 2 newtons. We know mass of A, which is 1 kilogram. We know mass of B, which is 3 kilograms. Of course, we know G because we're assuming we're on Earth. And what are our unknowns? What are we trying to solve for? We're trying to find F. And we don't know acceleration. Okay, those are our two unknowns. So I'm going to write an equation using Newton's second law around, I'm going to apply Newton's second law, which says the sum of the forces is equal to mass times acceleration. So I'm going to do that for each object. So this is equation 1. I'm going to do it around A. Okay, so I don't really like that. So anyway, okay, so the sum of the forces around A, that is equal to the mass of A times the acceleration. And oh, by the way, both of these objects are accelerating at the same magnitude, okay, because of the fact they're tied together. That is the point of coupled motion. Anyway, the sum of all the forces acting on A is equal to the mass of A times acceleration. And how many forces do I have that are occurring in the direction of motion? So we are assuming we're accelerating to the right. I only have one, so it's the force of tension. And I'm going to assume it's accelerating to the right, so it's positive, so we're good to go. Equation 2, the sum of the forces acting on object B. It's the mass of the B times acceleration of that object, which is the same as all the other accelerations. And what do we have? We have force minus force of tension. Now, I can add these up, and I get mass A plus mass B times acceleration equals force. That is the one that I'm looking for, okay? If you don't get opposite signs on your force of tension, then I guarantee you did something wrong. What am I trying to find? I'm trying to find F. So there's my unknown. This is what I'm trying to solve for. But look at what I have. I have acceleration in here, and I don't know it. But if I use equation 1, I can find A. I can find A by using equation 1. So I will rearrange equation number 1 for A. I find that A is equal to force of tension divided by mass of A. I know mass of A, I know force of tension. 2 newtons divided by 1 kilograms is 2 meters per second squared. Now I can use that value, plug it into what I will call equation 3, which we developed, and I will find force is equal to mass of A, 1 plus 3, this is in kilograms, times acceleration, which is 2 meters per second squared. Look at that, kilogram meter per second squared. That's a Newton, that's perfect. divided by the two masses added together. No, I'm done. So 4 times 2 is 8. Sorry, I lost track of what I was solving for. Force is equal to 8 newtons. Okay, let me just recap. So I used equation 3. I'm trying to find F. All I did was plug in the two masses, multiplied it times the acceleration that I just got, and I found that, number one, my units work out, which is wonderful, because that would tell you something's wrong if it didn't. Kilogram meter per second squared is a newton. So 4 times 2 is 8. This is the answer. Okay. 2.6 kilogram objects are connected by a thread that passes over a light frictional pulley as shown. The objects are initially held at rest. Okay, so can you imagine if I didn't have this 0.3 there originally, it's just sitting there, both the masses are the same, that would make sense that they're at rest. Then we put another object with a mass of 0.3 kilogram is added to one of them as shown, and the objects are released. That means that their masses are unequal now. We're going to have an acceleration that occurs. They want to know the acceleration of the 0.3 kilogram object. Okay, hopefully you see that acceleration is going to be this way and acceleration is going to be this way. Now, how about we redraw this pulley system and we just have one mass here that is 0.9 kilograms. And we have another mass that is 0.6 kilograms. And let's call this object A and object B. Okay, so I have 0.9 on the left and 0.6 on the right. I think we can solve it if we want to know that. So I'm going to draw some free body diagrams on object A. I have force of gravity acting on A, which is equal to mass of A, which by the way, A is 0.9 times the acceleration due to gravity, which is the same as the weight of A. And I have this force of tension. So this is my tensions. They're equal because the pulley is considered to be massless and frictionless. And let's make sure we know which direction acceleration is. It's downward. Then we have a free body diagram on object B. We have force of gravity that acts on object B, which is the mass of object B times acceleration due to gravity. That happens to be also the weight of object B, and that is force of tension upwards. And in this situation, acceleration is upwards. Now, here's my rule. Assume A is positive, okay? And all forces in direction of A are positive, okay? All forces that are opposite direction of A are negative, okay? So that's how I particularly solve it. The book actually assigns A as positive and negative, and then it becomes a total disaster. I have not found students to be successful, and nor does many other physics teachers. So if you just assign the direction of acceleration as positive, so we're just going to assume we're going to find the magnitude of acceleration, and then every force that is in the direction of acceleration is a positive force, and every force that's in the opposite direction of acceleration is a negative value, you'll get it right. Okay, so what are we trying to find? We are trying to find the magnitude of the acceleration of the 0.3 kilogram object. Isn't the acceleration of all the objects the same? So we're just going to find acceleration because every single one of these objects are accelerating at the same magnitude. So we're going to apply Newton's second law across A and B, and we are going to write our equations and go from there. So I'm going to sum the forces. I'm going to call this equation 1. Sum the forces on object A, and that will be let's do this in blue. So all the green is the free body diagram work. The red is my assumptions, and now I'm gonna apply second law, which is the sum of the forces is equal to mass times the acceleration. Okay, so here we go. First, I'm using method 1. I'm going to sum the forces across object A, which equals to the mass of A times acceleration of A. Now, which force is causing acceleration, which is in the direction of A? That is FGA minus force of tension. Equation 2, sum of the forces around object B. That is mass of B times A. That is FT, because that's in the direction of acceleration, and that will be subtract FGB. Now I can add all these up. I can also plug in the symbols for FG, which is the mass times acceleration due to gravity, and I will get MA plus MB times A is equal to MAG minus MBG. Notice the signs of the tensions are opposite, they cancel. And I can solve for acceleration, which will give me A is equal to MA minus MB. So the differences of the mass times the acceleration due to gravity divided by the total mass of the system. The differences of the mass, so that's kind of like the driving force. One mass is working for you, one's working against you, divided by the total mass of the system, and then times acceleration due to gravity. Okay, and I can plug in my values and solve. But just for chagrins, this is equation 2. This is what I call equation 3 after I've added them, right? Well, how would I, what if I did the sum of the forces on the system? Can't I do that? Well, what's my system? My system are the 2 blocks. So I have the mass of the system times acceleration. What are the external forces on the system? The external forces are force of gravity that are acting on object A and B. One of them's working with me, one of them's working against me. So the one that's working for me is the force of gravity on object A. The one that's trying to slow me down that's external to the system is the force of gravity on object B. Plug all those in, guess what you get? You get the same exact thing as what we did just now when I solved it, kind of a more piecewise approach. Mass of B. Okay, so I plug in those values. What do I get? I get acceleration is equal to, what's the mass of A? We defined A as 0.9 kilograms plus mass of B, which is 0.6 kilograms. I'm going to assume G is 10 meters per second squared for simplicity. 0.9 plus 1.6 is 1.5 kilograms. I will find that acceleration to be equal to 2 meters per second squared. Whichever method you use. This one, in my opinion, was the hardest one on here, maybe. Okay. I'm going to call this object A. I'm going to call this object B. I got 2 blocks. One, I don't know the mass. The other end is attached to a mass of 1 kilogram. It's hung over a massless, frictionless pulley as shown in the accompanying figure. Mass M, which we have as object A, accelerates downward. That's important. Acceleration is down. This acceleration is up. A couple of other things I know. I've got force of tension, and these are the same because the pulley is frictionless and massless. In other words, it doesn't have any inertial mass. I don't have to have any forces to accelerate the pulley. And the pulley's not putting any friction on the axle is not putting any friction on the pulley, which would also cause it to slow my acceleration down. Let me just clean that up. Okay. Okay, now, what do? Well, free body diagrams, folks. They're your friend. So this is A. I have Fg on A, which is the mass of A times acceleration due to gravity, same as the weight of A. Straight up is Ft. Free body diagram on B. Up is Ft, down is the force of gravity on object B, which is equal to the mass of B times the acceleration due to gravity of B, which is the same as the weight of B. This is my free body diagram on B. Acceleration is down, acceleration is up. We will assume that the magnitude of acceleration is positive, and every force that is in the direction of acceleration is considered a positive force, and every force that's opposite of acceleration is negative. Those forces that are perpendicular are not, like, which we'll do in the third one, we're not going to pay attention to. We're just going to focus on the forces that are assisting or resisting acceleration. Okay, so let's make a list of our knowns. What do we know? We know they told us the acceleration and they told us the mass of B. What are my unknowns? Well, I don't know mass of A and I don't know force of tension. Okay, so I'm going to come along, I'm going to apply second law. Sum of all the forces is equal to mass times acceleration. So let's do that. Let's sum, I'm gonna call this equation 1. Sum of the forces around A is equal to the mass of A times the acceleration. Oh, the acceleration in both is the same. Both of them have the same magnitude of acceleration. What forces are assisting the acceleration or in the direction of acceleration on object A? Well, that would be Fg of A, which we can go ahead and write MAG. Subtract the force of tension, that's opposite the direction. This is equation 1. Now I'm going to write equation 2. Sum of the forces around object B is equal to the mass of B times acceleration. What forces are in the direction of acceleration? Force of tension. What are opposite? Force of gravity. Well, what is that? Mass of B times G. I can add these two equations together. I will get MA plus MB, sorry, MA times acceleration plus MB times acceleration is equal to, notice, opposite signs, they cancel. MA times G minus MB times G. Okay, I should also just say over here unknowns. We know G, that's a known. What am I trying to find? I am trying to find, they want to know the mass of A. This is what I'm looking for. Force of tension was my other unknown. Force of tension is no longer in this equation. I can solve for the mass of A. How do I do that? Well, I have to subtract mass of A. I need to get A by itself. So I got to subtract mass of A from both sides, mass AG from both sides. I have to add MBA to both sides. This is just simple algebra here. And what does that simplify to? MA times A minus MA times G is equal to negative MBG plus, did I do something wrong there? Kind of feel like I did. Hold on. Yep. I see what I did wrong. In order to get rid of MBA on the left-hand side of the equation, I have to subtract it. So that was a minus MBA. And that should have been a minus MBA. Okay, continuing on. That is a minus MBA. Okay. I can factor out MA from here, and I get MA I should be using, it would probably be good if I kept the big capital A. There we go. Okay, MA times our acceleration minus acceleration due to gravity is equal to negative mBg minus mB times acceleration of the system. I'm getting there, almost there. You never knew you were going to use so much of your algebra again. Divided by acceleration of the system, which we know, subtract G. Mass of A, negative. What's mass of B? 1 kilogram. I'm going to use 10, by the way, minus mass of B, 1 kilogram, times what they tell us acceleration of the system was, 5. Those are in newtons. So this is in units of newtons, kilogram times meters per second squared. All that's in newtons, so I'm feeling pretty good about that. Divided by the 5 minus 10, that's a negative, good. And that's going to be divided by meters per second squared. Newtons, which is a meters per second squared times kilogram divided by meter per second squared, gives me an answer in kilograms. That's perfect. Mass of A, come on. Mass of A is found to be 3 kilograms. Could have solved it too by doing the sum of the forces on the system. Just quick, sum of the forces on the system is equal to the mass of the system. Mass of the system is MA plus MB, right? Times the acceleration of the system. Two forces that are external of the system. One of them that's creating acceleration, which is force of gravity on A minus the force of gravity on B. You would have had to plug in all your symbols and solve for mass of A. You would have gotten the same exact answer. You might find that more efficient of a process. Last problem. Should have told you, this is my fault, should have told you to have your answers in terms of M1, comma, M2, comma, M3, U, and G. Okay, very common in an AP exam type question, no numbers, just symbols. So what are we trying to find? We want, let's see, we have 3 masses, M1, M2, M3. We know that we have friction because they gave us mu, and it's kinetic friction, okay? So we're not gonna type, we have to have mu, don't put mu K, whatever they tell you in the problem, you have to have the same exact symbol. What would be the upward acceleration? Here's the question. Upward acceleration of the small mass M3. Come along here, and we know we're going to be accelerating upwards. This has to be accelerating that way. This has to be accelerating downward, okay? Now, we've talked about the easiest way to do this is to, because there's so many problems, is to sum the forces on the system, which will be the mass of the system times the acceleration. And now I need all of the external forces. I need the sum up all the external forces on the system, right? Let's see, I want to sum the external forces here. Okay, so I don't know how many, but let's think. Let's draw a dotted line and call my system the 3 blocks, the string that attaches them. Those are my system. Okay, so this is my system. So forces that are external are force of gravity acting on all those blocks and force of kinetic friction. And here's why force of kinetic friction is external. That is a force that occurs between the surface of the block M2 and the table. That table isn't accelerating. So there is an external force that's being imposed on mass 2 that is not a part of the accelerating system. The system is the 3 blocks and the strings between them. So if you do that, you will find the forces external, okay, to the system. I think that's really important. External is the mass of the system. Well, what's the mass of the system? M1 plus M2 plus M3 times A is equal to, I got to sum up all the forces in the direction of the acceleration that are external. Well, if I drew a free body diagram on mass 3, the one that's external is FG3. The internal one is that tension force. And is this in the direction of acceleration, force of gravity on mass 3, in the direction of acceleration or against it? It is against it, so it's a negative. So minus FG3. Now let's look at mass 2. This one's confusing. So if I know that the acceleration is to the right, where is force of kinetic friction? It has to be opposing motion, correct? So if I had a free body diagram, I'd have Fg on 2, F normal, force of kinetic friction, that force of tension to the right, we'll call this T1. So we'll call that T1. And then we'd have force T2 to the left, okay? So that force of gravity that's acting on block 2 is not in the direction of acceleration. It is not assisting us in any way, shape, or form. We are only summing the forces in the direction of the acceleration. So the only force that's external to the system is related to mass 2 is the kinetic friction, and it's in opposite direction of acceleration, so I have to subtract it. Now I go to mass 1, and if I look at the forces acting on it, I have this FT2, okay? Yes, okay. And there's only one external force that's acting on mass 1 that's in direction of acceleration, so it's a positive. And that would be plus FG2. So acceleration is equal to, I'm just going to plug in correct symbols now, mg3 minus force of kinetic friction plus mg2g divided by the mass of the system. Now, one last thing. We can't leave it in terms of force of kinetic friction. By definition, force of kinetic friction is mu Fn. What is Fn on block M2? Well, that's M2G, because you'd have to solve for Fm, and hopefully you're starting to get good at that. So I'm just going to go ahead, replace that kinetic friction with what it actually is, which is mu M2G. That's your answer. You knew all your values, you'd be able to solve it. So got one mistake I see. I'm just going to rework this problem. All right, last problem, and it's a more challenging one. If you can understand this concept, you're doing just great. All right, here we go. I have three masses as shown in the diagram above. If the coefficient of friction between the large mass M2 and the table is mu, what would be the upward acceleration of the small mass M3? The mass and the friction of the cords and the pulleys are small enough to produce negligible effect on the system. Okay, they told us we're accelerating upwards, which means this guy's got to go that way, which means this guy is accelerating downward. Okay, they told us that I have friction here. How did I know that the force of kinetic friction is pointing in that direction? Well, if I'm accelerating to the left, my kinetic friction has to be opposite of motion parallel to the surface. So I could draw three free body diagrams on these. Force, this is T1, I'll call this T2. Force T1, M1G pulling down. On block 2, I have force normal, M2G coming downward. I have force of T2. I also have, I could just go ahead and add another force of kinetic friction. And to the left, I have FT1. And then the third block, I have M3G. I have force of T2, and that's it. Important. Acceleration is up, acceleration is to the left, acceleration is down. Now, it is much more efficient to sum the forces across the system. Sum the forces across the system, and we want all the external forces. Whenever we sum the forces on the system, the only forces that cause acceleration are external. Well, what is the system? By definition, like if it would be nice to know what the system is, because I can only sum the forces, well, that are external to the system. The system are the three blocks. They're the things that are accelerating, and the chords that are between them. So we can put and chords, I guess. Okay. So what are the external forces that are in the direction of acceleration? Okay, so let's go and highlight on our free body diagram things that are external. So let's look at mass one free body diagram. Well, force of gravity is external. Force of tension, T1 on that block is internal. So that's not an external force. So let's look at the next one on M2. Well, acceleration is to the left on M2. I am not concerned about forces in the y direction. So force normal and M2G are not in the direction of acceleration. I'm only concerned about the forces that are external to the system that are in the direction of acceleration, and that would be the force of kinetic friction. Why? Why is that an external force? Well, because force of kinetic friction is caused by the block and the tables. So the table's external. Table's not, it's almost like somebody's hands reaching in there to try to slow it down, but it's not. It's a table. It's a contact force that has occurred. That is external to the system. And that table's not accelerating. Then look at the third block. What's external to it? Well, that would be the force caused by the earth. That's external to it. That force of tension is internal to the system. That string is accelerating and not causing any external force. So there's my forces that are external. Those are my external forces. I'll highlight that in love. All right, now, so let's sum the forces that are external. Well, I need the mass of the system, which is M1 plus M2 plus M3, times the acceleration of the system, which is the same for every one of those blocks, is equal to, now every force that is in the direction of the acceleration is a positive. Well, there's one, M1G, and then every force that is opposite the direction has negative, minus F kinetic friction minus M3G. Okay, now I got to come over here and discuss force of kinetic friction. Okay, kinetic friction. What is the definition? Mu K times Fn. Well, what is force normal on block 2? Well, hopefully it's on a flat surface. I can solve in the y direction, and I find that force normal is M2G. Now, per their instructions, they gave me mu K as the symbol mu. Sorry, M2. So I can only have the symbol mu, because I'm going to use the symbol they gave me, unless you gave them a legend and changed it, but just use what they gave you. That's the best thing. Okay, so here we go. Mass 1 plus mass 2 plus mass 3. That is the total mass of the system times acceleration is equal to M1G minus, well, mu M2G minus M3G. I'm solving for A. A is equal to M1G minus mu M2G minus M3G divided by the total mass of the system. Now notice, there's the answer. I just want to point out something. We just solved for something very similar up here. I think it was the second one where the acceleration was equal to the difference of the masses times g divided by the sum of the masses. So let's look at this one. Let's rearrange this just a little bit. This is the difference of the masses, and one was the greater mass. But then I just had to take out the force of friction, and then I divided by the total mass. So it's actually very similar, and maybe you're starting to see that. The difference of the masses times acceleration due to gravity divided by the total mass, and then if I have friction, I got to subtract out what that friction is. Okay, hope that makes sense. That's what I got. Come see me if you have questions.